Hello, my name is Nastasia Masalova, and this is my lab report on the topic of the Newton's Cradle. So, the Newton's Cradle was designed by French scientist Adam Mariotte and named after English scientist Newton. The Newton's Cradle demonstrates the conservation of momentum with ringing spheres. The main goal for my PHYS lab is to analyze the motion of the Newton's Cradle spheres to observe the conservation of momentum in the real world. Before I elaborate on the lab and the results, I want to cover several concepts and formulas that we will need for analyzing the motion. To predict the ball's motion, we need to know the net force acting on it. There are two forces acting on the ball, the force of gravity and the force of tension. The force of gravity is gravitational constant multiplied by the mass, and the force of tension can be found from the second Newton's law, and equals to mv squared over r plus mg cosine theta multiplied by n hat, where r is the string length. Cosine theta equals to r minus y component of position divided by r. Additionally, we will need to know p hat, which is the unit vector of velocity, and n hat, which is the cross product of p hat and the unit vector in OZ axis. Knowing the net force, we can implement velocity update and position update formulas for creating a computational model. We will also need the momentum formula, which equals to mass multiplied by velocity. By the conservation of momentum principle, the sum of final momentum should equal to the sum of initial momentum. To get data about the object position in the video, I use a tracker application to analyze the motion. I created around 80 points to track the object's x and y components. In my experiment, I decided to simplify my model by creating only 2 balls instead of 5 as in the real Newton's Cradle. One model ball represents the falling ball from the right side of the cradle, and the second one illustrates the pushed ball on the left side of the cradle. Then I defined the position vector of the first ball by taking this data from tracker. I also defined cosine of theta with initial value of 0.49 and the sine of theta with initial value of 0.87, which I found mathematically. I also defined the length of the string. Finally, I used the formulas described before to create initial p and n hats, as well as gravitational and tension forces. I also created v final variable, that is the final velocity of the first ball at the bottom of its trajectory. I found this value from the energy principle, knowing that potential energy is fully converted into kinetic energy. After that, I created 2 while loops. The first one defines trajectory of the first moving ball, and the second one defines trajectory of the second ball. In each while block, I updated the value of p and n hats and values of forces acting on the balls. I also used the position and velocity update formulas to make the model ball smooth. And after the first while loop, I defined the velocity of the second ball to be equal to the final velocity of the first ball, based on the conservation of momentum principle. After finishing the coding part of the lab, I ran the program and observed the motion of the balls. For my final part of the lab, I compared the speeds of the model and observed balls. We can say that the curve of the observed ball's speed is rough, but its overall pattern resembles the speed curve of the model. The difference mainly occurs because I didn't know the initial numerical values of the ball's masses and radiuses. We can also see that at the time of 0.71 seconds, there is a discontinuity in the blue curve, but the values of the endpoints are very close. This shows the validity of the conservation of momentum in elastic collision. The second ball got the velocity from the first ball, which made it move up. Thank you so much for watching my video. This is the end of the presentation.